This segment we're going to work a problem where we've got a gas mixture in a closed system with constant composition. So here we go. We've got a gas mixture in a piston cylinder assembly. We're given the mass of each of those components, and I'm asked to find, part C and D are asking us to find the heat transfer and the change in entropy if the temperature increases from 70 degrees Fahrenheit to 150 and the pressure is held constant. So those temperatures and pressures that were given, those are referring to the mixture, the overall mixture, the overall temperature and pressure. If I use Dalton's model, I can say, well, the temperature of the mixture and the components are equal, but I'm not saying that for the pressure. I would define partial pressures. So this pressure that they're telling me about, it's the overall pressure, not necessarily the component pressure. So the pressure here, the overall mixture pressure is constant. I don't really know what the pressure is. I just know that it's constant. Here are the things that I need to find and the units that I need to find them in. And it tells me I can assume that my mixture behaves as an ideal gas with constant specific heats, but I'm not actually going to make that assumption until I have to. So for our part A and part B, I don't. I just need to put things in a table and calculate my mass fractions and my mole fractions. So I've got two components. I've got nitrogen and helium. Next column is my mass. So I've got 2 pound mass and 3 pound mass. Then I need to look up my molar mass, and I can look that up in table A1E. So I've got that for nitrogen and for helium. And if I divide the mass of the component by the molar mass of the component, I get the number of moles of the component. So 2 divided by 28.01 is 0.0714, for example. Then I calculate my mole mass, or my mole fraction. So I've got the number of moles of each component. I just need to get the number of moles of the mixture, and that's just 0.0714 plus 0.7494, and that gives me 0.8208. So the mole fraction is going to be the number of moles of my mixture for each, or the number of moles of each component divided by 0.8208 pound mole. So I've got my mole fraction. I need to get my mass fraction. So the mass of my mixture is just 2 plus 3. So 2 divided by 5 is 0.4. 3 divided by 5 is 0.6. And so now I have my mass fractions and my mole fractions. A lot of times I'll just leave off those units, but I'm going to leave them here just so we can see when we start calculating things with part C and part D where those units cancel out. I think it's helpful. So, okay, so let's keep going. So for part C, we want to find the heat transfer in BTU, and if you were in Thermo 1 and I was asking you to find the heat transfer for a substance in a piston cylinder, you would say, I'm just going to apply my first law, and you would be correct. And then you would say, which one do I choose? Do I choose the first law for an open or closed system? I've got a closed system. You would also be correct. So I'm going to apply my first law for a closed system here, and you will notice that I am back to sign convention, which is what you were used to in Thermo 1. So when we talk about cycles, we use subscript conventions. So you have a Q in, Q out, W in, W out, and all of those W and Q terms are positive quantities, and the subscript is what tells you whether it's going into or out of the system. Here we're going to go back to sign convention. The choice of subscript and sign convention, it's just a matter of convenience, and for these types of problems, it's more convenient, I think, to put things in terms of sign convention and use the sign to tell you whether heat is going into or out of the system or W is going into or out of the system. So if Q is positive, it means heat is going into the system. If W is positive, it means that work is going out of the system. So make sure you're familiar with that. And from this point on in the semester, we're going to be using sign convention. So there you go. All right, so here's my first law, and I'm going to go ahead and get rid of kinetic and potential energy changes because, well, I don't even know anything about them anyway, and so I can't calculate anything about it if I wanted to. So let me drop those guys. And now the work, I can't get rid of him because I have boundary work. I'm increasing the temperature of this gas. The pressure is being held constant, so I'm allowing that gas to expand, and so I'm going to have positive boundary work. I do have an equation for boundary work. I just need to make the assumption that it takes place as a quasi-equilibrium process. So that's the integral of P delta V, or P dV. And since my pressure is constant, it's going to come right out of that integral, and I've got P delta V. So P delta V, I put that on the other side of the integral sign, or the equal sign, and I've got delta U plus P delta V. That's just my definition for delta H. And if I were still in Thermo 1, I would put this in terms of delta little h because I can look those properties up. Those are usually tabulated for me. All right, so at this point, I'm out of Thermo 1, I'm into Thermo 2. I'm dealing with these ideal gas mixtures. And so I know that this delta H for my mixture is going to be a function of the components. So I look on my equation sheet, and there's my equation for delta little h for an ideal gas mixture. All right, so it's a function of the mass fractions and the delta H for each component. Now if I had tables for nitrogen and helium that gave me H values as a function of temperature, I could use those, but I actually don't have those in my book. So I'm going to use the next best thing. I'm going to use the assumption that specific heats are held constant. So, or the specific heats can be taken as approximately constant, that they're not a function of temperature. They don't vary with temperature. And I'm told I could do that in the problem statement anyway. And it's not really a bad assumption to make regardless, because my temperature change is really not that big. It's on the order of about 100. So, okay, so with that being said, let's put that delta H in terms of Cp delta T. And I have a little subscript I after each one of the components, or each one of the things that are referring to something about the component. I am going to drop the component I subscript from the temperature, because with Dalton's model, I am modeling it such that the temperature of the components and the mixture are equal to one another. So I guess that's really it. And now I'm ready to plug in some numbers. And I've got all the stuff that I need. So my delta T, I went ahead and brought that out on the to the outside of the equation because delta T is the same for each one of those components. But I know the mass of the mixture. I know the mass fraction of each of the things. I know the Cp for each of the components. And I just do the math, and I get 337.3 BTU. That's it, yeah, and my units work out. That's it. So now I'm ready to look at part C. So I need the change in the entropy. It's m delta little s, and that delta little s on my equation sheet for an ideal gas mixture, here we go. It's a function of the mass fraction and delta little s for each of the components. And because I have an ideal gas with constant specific heats, I'm going to use the delta S equation for an ideal gas with constant specific heat. So it looks like this. So you've got a mass fraction, or you got a mass fraction, but it's multiplied by delta S for an ideal gas with constant specific heats. So I get a Cp natural log T2 over T1 minus R natural log P2 over P1. So, all right, well, let's start kind of looking at each of these components. First thing I'm going to do is I'm going to drop the subscript I from the temperature, because once again I'm using Dalton's model, which says the temperature of the component and the mixture are the same. Now let's look at that pressure. Well, I know that the pressure is, I don't know anything about the component pressure, or I'm not given that information. However, I do know that by combining the ideal gas law and Dalton's model, I can put that partial pressure for each of the components at state 1 and state 2 in terms of the mole fraction at state 1 and state 2. Now, I have no, it's a closed system, well, that doesn't have anything to do with it, but it's there's no chemical reaction going on. So I start with 2-pound mass of nitrogen and 3-pound mass of helium, and I end up with the exact same thing. So I don't have any chemical reaction. You'll be told if there is a chemical reaction, but there's no chemical reaction between those two gases, and so your mole fraction for each component at the initial and the final state are going to be exactly the same. Furthermore, so Y2 and Y1 for each component are the same, so those are going to cancel out. Furthermore, I know from the givens that P2 and P1 for the mixture are exactly the same. So that last term right there, it's going to be R natural log of 1, which is just going to go away. So there we go. So there's my equation. I've got everything except I've dropped that R natural log of P2 over P1 because it has gone away. All right, so now I guess I'm ready to plug things in. I got the mass of my mixture, I've got the mass fraction of each one of those things, I got the CP value for each term, and then I just plug in the natural log. I just need to make sure that my temperatures are in terms of degrees Rankine. And I've got 0.593 BTU per degree Rankine. So, all right. Well, thank you for watching. Let me know if you have any questions.